In this video, we're going to prove what somebody might call the homogeneity of sequence convergence. That is, if you have a sequence A converging to some limit k, and then you multiply the sequence by a constant, meaning you're just going to multiply each term in the sequence by that constant, then that new sequence is going to converge to, well, you just take the original converging limit and multiply it by that same constant u. All right, so the proof, much like our proof of the additivity of sequence convergence, is going to come down to, well, first writing down the limit for the definition for sequence convergence, and then showing that this new sequence UA will also satisfy that same definition, except possibly using the Inspired Choice Theorem. So let's start by writing down our definition again. So since A is converging to K, we know that there exists an eventually function, right? So a function m from our domain of closeness measures how close we need to get to the integers. This will tell us how far we have to go out in the sequence, such that if epsilon is some positive real number, and if we go out past the eventually number for epsilon, greater than, then the difference between all the mth terms in the sequence and this proposed limit k is less than epsilon. Okay, so again, this is just the definition of A converging to k. All right, so now we want to show that this sequence UA converges to UK. So again, go back to the definition, we need to find an eventually function. And the eventually function is going to be very, very much related to m. Very much related to m. So let's define an eventually function. We'll give it a new name. Define n from our domain of closeness to our codomain of eventually. And I need to tell you what epsilon is going to get mapped to. And strangely enough, it's actually just going to get mapped to the same eventually number as m would have mapped it to. All right, so in actuality, n as a function equals m. It's not really a new function at all. Okay, so let's see if this actually will satisfy the definition, or at least the Inspired Choice Theorem. So let's take an epsilon from our set of real numbers, and if little n is bigger than n of epsilon, which is, again, just m of epsilon, then, well, we want to see how close the nth term in the sequence, which is now UAN, is to the proposed limit UK. All right, well, I notice I have a u in both of these terms, so I'm going to factor that out. So I get u times an minus k. And now, because the absolute value is multiplicative, I can break this up as the absolute value of u times the absolute value of an minus k. Okay, but we know that we are past the eventually number for epsilon with respect to m, which means that an and k are within epsilon of each other. So this is less than epsilon because we are past the eventually number for epsilon, which means that this product is less than the absolute value of u times epsilon. Now u is some positive, well, I guess in principle, I guess it could be a 0, right? Let's handle that case separately. Let's treat this as a positive real number, all right? Since, well, and of course we can say that because we have absolute values, all right? Because it's a positive real number, and it doesn't depend at all on the epsilon we chose, right? This u is just some fixed number from the beginning. Then we can use the Inspired Choice Theorem, which says if the difference, right, between the sequence and the proposed limit is less than some positive number times epsilon, then you get convergence anyway. So by the inspired choice theorem, U, A bar, converges to UK. Now I should mention what does happen, right? This assumes, of course, right, that U is not equal to 0. What if U was equal to 0? Well, then our original sequence would just be 0, 0, 0, etc. And the proposed limit would be 0. And of course, the 0 sequence does converge to 0. All right, so we can add that as a little addendum at the end. If U equals 0, then UA bar is equal to the sequence of zeros, right? Or what you might call the 0 sequence. And that does converge to 0, which is equal to 0 times k. All right, so that's just a little special case. So once again, the inspired choice theorem prevents us from having to make any sort of an inspired choice. All right. Now, we could have gone back and made the inspired choice if we wanted. We could have said, well, okay, what do we really need? We need to somehow get rid of this absolute value of u at the end. So instead of this being less than epsilon, I want it to be less than epsilon over the absolute value of u. So what the expert might do is, instead of defining n to send epsilon to m over epsilon, they might send epsilon to m of epsilon over the absolute value of u. All right, and then down here, of course, we would have been able to now say that instead of being less than epsilon at this step where an, we took the distance between an and k, we would have said less than epsilon over the absolute value of u. And now over here, we would have had absolute value of u times epsilon over the absolute value of u, which is equal to epsilon. But you see, man, that's just so much more extra work. Let's just be inspired by not being inspired.